Okay, I think we'll get started. David, I assume I have 20 minutes, is that correct? Yeah, so it's 25 to, okay, good, so I'll stick to my time. So the title here is a trap for unwary, what can go wrong when installing instruments. And I have 20 minutes to introduce you to that. So you can imagine that there would be hours and hours of the details on which we could discuss. I've selected a few topics into those broad categories, piezometers, inclinometers, and so on. So I will not cover everything for everything. I just selected a few specific topics that I thought were useful to bring up here today. So let's start. So it will be those 5 points that I will be discussing. First of all, I allow myself to introduce the platform for which I work, because I realized I didn't do that yesterday. So Terra Insights is the umbrella name for 5 geotechnical monitoring companies. So we're a group of geotechnical monitoring companies. So you might recognize some names in there. RST Instruments is the traditional piezometers and inclinometers. Measurement is the shape array. 3View Geomatics is the satellite INSAR. Syscom is the strong motion and ambient vibration monitoring devices. Navstar is the visualization software and GNSS, and Ground Probe, that was mentioned earlier, is the ground-based radar and ground-based INSAR company. And very recently, we've been acquired by Orica, so we're now part of Orica Digital Solutions. So mates, we're an Australian company. Starting with piezometers. Actually, I thought let's take the example of the project that we have on which we're planning the monitoring program. So on this figure, you can see that I sell vibrating wire piezometers. So, so I put a bunch of them in there. But this being said, let's assume that you're deciding to put a multi-level installation of piezo's into any one of those cross section. And by the way, I thought that in the next panel that we will have, we could discuss how we would drill the boreholes to install those instruments. But for now, let's just consider what can go wrong apart from the drilling on installing those piezometers. So the idea for installing a multi-level installation like that is because you'll probably be interested to assess the flow network, the groundwater flow or the water flow network into the tailings, and therefore putting a multi-level installation by which you can verify if there is a vertical gradient between those elevations. That means a flow that goes down, or a flow that goes laterally. In other words, the real flow network that is happening into the tailings. You need a certain number of measurement points. So it's probably a good idea to try to do a multi-level installation instead of having separate boreholes for each of the piezos. So if we review, and I think this is probably an image that many of you have seen before, and just to repeat that we have basically 3 options. Traditional Casagrande standpipe piezometers, and a lot of piezometers are still installed in tailings dam as standpipes. And then simply putting a vibrating wire piezo into a borehole, but this time in a sand pack and a bentonite seal. And this here is a vibrating wire piezo. Here it was a Casagrande filter with a vertical PVC pipe. This is simply a signal cable, electric signal cable, or fully grouting the piezometer and of course putting many piezometers into the same borehole. So these are the 3 options, and if we go through each of them, starting with the Casagrande standpipes. So as I mentioned, it's maybe the method, the approach that your drillers are most familiar with, although they might be quite familiar with the sandpack and the bentonite seal method. But let's start with the Casagrande standpipe. So all in all, it's proven reliable over the years. Many piezo's are installed that way. Except that it can prove to be difficult to do a multi-level installation. I've seen multi-level installations of 4 or 5 Casagrande standpipe in a 15 centimeter diameter borehole, but there was strong evidence of hydraulic conductivity between the various points. So it's definitely not recommended to do more than 2 or maybe 3, but even 2 in general. 2 is the maximum that you should consider into a borehole. Don't forget also the bentonite seal under the sand zone. So these type of representations, there's something they don't show, is that you need a bentonite seal under the sand pack. Otherwise, you're not isolating a zone on which you're measuring the groundwater. You compromise the reality that you want to measure at a specific horizon. So don't forget the bentonite seal below, but at the same time, the bentonite seal below makes the installation, even for this one here, the sandpack and bentonite seal, makes it way more difficult, because then you have to do, at the bottom of the hole, you have to do a bentonite plug, pour the sand, bentonite plug, eventually grout the distance that there is in between, or simply fill with bentonite all the way to, well, in that case, it's a grout, but you can also have bentonite all the way to the next sand zone. And there is the well-known problem of bridging of the bentonite into the borehole, and that's the pain of all. So how to avoid this bridging? Number one is don't use bentonite powder. Use bentonite chips, and coarse bentonite chips, more the 9 millimeter size instead of the smaller one, or bentonite pellets. But again, bentonite pellets, don't use the small one. Don't use the 6 millimeter one, use the 9 millimeter one. There are tests that show that you have way less bridging with coarser bentonite pieces and no dust than with bentonite powder. So that's that for standpipes, I believe, and zone installation with the sandpacks. And now the grouted method. So the grouted method has become very popular in the last 20 years. Maybe 50% of the, maybe, I don't know in reality, but maybe 50% of the piezometers are installed nowadays grouted in tailings dams, maybe less, maybe more, I don't know in reality, but it's very prevalent. So that method at the beginning was seen as the miracle to the solution to all installation problems, because conceptually it looked very easy when it was introduced, especially in 2003 by Mickelson and Green, to say that, okay, it's easy, mix of 2.5 in weight of water, 1 part of cement and 0.3 part of bentonite, you mix and you have a grout that looks. You grout that into the borehole, and you can do a multi-level installation by having either, adding many piezos into the borehole and grouting the whole column, and there will be no hydraulic conductivity in between the piezometers, and you will be simply monitoring the pore water pressure at the elevation of the piezo. And this was really defended during a long time by the proponents of the method, including, for those who have read a little bit the literature, including the very well-known paper by Contreras and colleagues in 2008, where they proved by modeling that you could have a discrepancy of 3 orders of magnitude between the permeability of the grout and the permeability of the enclosing soil. And you would still have no vertical flow, vertical hydraulic connection into the borehole. So that means in a tailings that would have a 10 minus 8 centimeter per second permeability, you could have a grout of 10 minus 5 centimeter per second and still be okay. And this has now been proven to be true only in very exceptional circumstances that you probably don't have in your tailings dam. And now I will not bother you for a long time with the next 4 slides, but I encourage you to read the reference that that is here, and maybe to go a little bit through the slides that I will show here. But this is part of an effort that we have done. I'll come back in 1 minute to prepare a white paper on fully grouted piezometers. So this is a common situation that you have in tailings. It looks strange, but it's a common situation that you have in tailings dams, by which you have an impervious material, the clay, and then possibly a more pervious material above, and you're building rapidly an embankment. So this model, numerical model, simulates the rapid placement of a 5 meter of material over an existent formation of 20 meter, consisting of 10 meter of sand and 10 meter of clay. In that case, because the clay is very impervious, we all know that we generate a vertical flow. The flow is vertical downward. And the borehole, which is here, in which you've grouted the piezo, in that should be the same pore pressure as in the far field. Otherwise, you cannot say that the borehole or the piezo in the borehole is measuring the actual pore pressure that prevails in the rather impervious material. So it has to be the same. So when you run the model, especially when you run the model, the numerical model in transient flow conditions, which is the reality, there is a transient flow condition with this vertical flow that is created by the rapid construction of the embankment. It gradually stabilizes. So when you run the numerical model on that, you realize that during the first year, basically, you have an extremely high error. Here, the error is 7 meter over 10 meter. That means a 70% error in the determination of the pore pressure into the borehole. So the piezo is absolutely not reading what's happening. It's completely underestimating the pore pressure into the clay by 70%. And it takes, this is a semi-log here, so it takes here at 1,000 days, you're better, because here, but not so much actually. The error is between here and here, so you have to look at the same symbol. Yeah, between here and here, you still have 4 meter of error or 3 meter of error, 30% after 1,000 days. So that's for a ratio of 3 order of magnitude, 1,000 between the two. So 1,000, 3 order of magnitude is not good in tailings dam. You need to be better than that. If you do a ratio of 10 between the permeability of the grout and the enclosing material, in that case, your error is minimal. Now it's 5% after 10 days, and it's virtually zero after 20 days, and after that 1,000 days, it's so the conclusion jumps to the eyes that the permeability needs to be closer to the permeability of the enclosing ground. These are 2 case studies that confirm that really you need a proper match of permeability, otherwise it doesn't work. And I'll let you read those 2 case studies. They will be in the package that you will receive. And I'm jumping immediately to, and this is what Manuel was asking me to refer to you, is to the white paper that we hope to be able to publish in 2025. It's been an effort of the committee of USSD, US Society for Dams, on monitoring dams and their foundations. So that's our dam surveillance committee, if you will, of USSD. And it's been 5 years that we've been working on that and collecting a lot of information, doing numerical modeling, collecting, reviewing all the available literature and so on. And we hope to publish in 2025. And these are the proposed conclusions and recommendations that we are suggesting to the community. We're still at the peer review stage of all the work that we have done, but these are the recommendations that we're putting forward to the monitoring community. So bottom line, it says you need to have a 10-time permeability ratio, not more than that. You should test the grout. These are the ASTM methods to use. In most cases, or in many cases, it can be very useful to conduct numerical modeling of the flow network that you're anticipating in the borehole, but using a model that allows, and nowadays all those numerical models do that, that allows for transient flow, not only steady state. Steady state will show you the conclusion after 1,000 days or 3,000 days, but you want to know how performing will be your piezo's during all the days before that. So you have to do it in transient flow. But we have some good news. And you know what happens when people test the grout for their piezo's is they do the same thing as for concrete. We all learn at school, that at university maybe, that you test the compressive strength and the properties of concrete after 28 days, right? It's always 28 days. So people have always done that, testing the grout at 28 days. 28 days is here, actually, 28 days on that scale of 1,000 days. And a grout, especially the grout, which is the most ubiquitous, the 2.510.3, the blue here, is 10 minus 8 that's meter per second. So it's 10 minus 8 meter per second, so equivalent to 10 minus 6 centimeter per second. But look at what happens after 800 days. It's 2 orders of magnitude more impermeable than it was at 28 days. So the curing reaction is slowed down apparently because of the bentonite, but keeps happening. And after a couple of years, you're way more impermeable than what you thought before. But you cannot allow yourself that. You don't want to wait 2 years until you can say, yes, my piezo's are functional, that they read their actual pore pressure. But we can say that it's going towards the right direction. It's not going towards the wrong direction. So that's an advantage. So that's what I add on piezo's. Cabling, I think we'll come back in the next section to say a few words about cabling, because instruments fail very often because of the cable. The cable gets damaged, that gets cut in by trucks and so on. So how to protect the cable, how to do the trenches and so on, but we'll come back on that. Do you need a reinforced cable or a standard cable? In some cases, you need a robust cable. So we'll come back on that aspect also. Inclinometers. Inclinometers, basically, you have two things to decide. Is number one, how you will drill the hole, but that we will come back a little bit later on that. So how you will drill the hole, you have various options. And how you will fight buoyancy when you install the casing. Of course, you need to have the casing as straight as possible. Vertical within 1 degree is an old recommendation. Nowadays, even if you're somehow inclined, the in-place inclinometers and the inclinometer probes don't have the cross axis that they used to have many years ago. Many years ago, it was difficult for the manufacturers to put the sensor exactly in the X and Y direction. But nowadays, it's all better. And actually, it's all corrected digitally in the microcontroller of the sensor. So the vertical of 1 degree is a little bit less important. Don't go 30 degrees, but more than 1 degree is okay. But it's especially that you need a strategy for buoyancy. You need to anchor the casing at the bottom, because otherwise a casing, even filled with water in a cement bentonite grout, because of the discrepancy in the densities, will have an uplift of 1 kilogram per meter. So for a long casing, that starts to be quite a lot, and you cannot fight it from the top because otherwise you'll snake the casing into the borehole. It has to be installed anchored from the bottom. Grouting for the case. Nowadays, most people use the same grout for the casing, inclinator casing, as for piezometers. That part, I'm okay with that. In theory, it should be stiffer for installations in rock, but I'm quite okay with the same grout as for the piezometers. Now, the big question as well is, can you install a piezo in the same borehole as an inclinometer casing? So, can you do it? Yes, you just have to do it. Should you do it is another question. So, again, these are the proposed recommendations that we will have in the white paper, saying that yes, you can do it. It's a cost-saving factor. Quite a few people do it, but you should take into account that the experience shows that the water in an inclinometer casing gets out of the inclinometer casing. How? Maybe through the couplings, most probably through the couplings, actually. So even if there is an O-ring, even if there is glue, even there is a tape, water makes always its way. And in certain instances, it's been shown that it corrupts, it affects the piezometer readings. So at least put the piezometer in between two couplings. Yeah, put a spacer between the piezo and the casing, yes. But if there is a large displacement, that's when you need an inclinometer, when you possibly expect large shearing displacement, then the grout could start cracking, and then you're creating an hydraulic conductivity along the casing. So yes, you can do it, but maybe or probably you should not do it. Deep inclinometer installations, I will jump over that one. It's more for rock slope than for tailings, but deep inclinometer installations are possible. MEMS in place inclinometer, all I wanted to show to you is, because we've talked about that yesterday also, installation and so on. Don't neglect the importance of the connectors between the sensors. That's a point where strings of inclinometers can fail because, again, in the inclinometer casing, there is water. So don't neglect the importance of properly connecting the connectors. How much lateral displacement can be measured by an IPI? That's a question we get very often. An in-place inclinometer with a 2-meter sensor length can accommodate up to 68 millimeter of deformation, assuming that the casing deforms with a constant radius of curvature. If it's a 70 millimeter casing, or 85 millimeter casing will accommodate 93 millimeter. So take that into account if you're going to use in-place inclinometers with a long length.
2 minutes.
2 minutes. Okay, so sorry, nothing on the settlement systems, but you'll have it. Data loggers. All I want to say about data loggers is that, and we'll have a presentation on that a little bit later. All I want to say is that traditionally we had central data loggers with long cables converging to the central data logger. Nowadays, most manufacturers offer IoT solutions where you have, or based on IoT approaches, where you have a gateway and portable small data loggers that communicate by radio to the central gateway. And this is a big advantage for our field installations because I don't know if some of you have seen these type of maps, but that's a NASA satellite a few years ago that counted the number of lightning flashes per square kilometer per year. And you see that along the equator, but even along the tropics in many places in the world, you have more than 100 lightning strokes per square kilometer per year. So lightning is a problem. So either you do difficult to realize lightning protection with lightning protection components at each borehole, grounding everywhere, junction boxes, and so on. And the reason for that is that when lightning strikes, okay, so this is an installation with long cables that converge towards the data logger. So when lightning strikes, it generates very high voltages, 100,000 volts or something like that, that travel very fast at the surface of the ground. That means that you'll have between two equipotential lines. This one might be at 100,000 volts. This one might be at 50,000 volts. Along that short length of cable, V equals Ri. You remember that from school. Voltage equals resistance times amperage. You generate very high transients that damage the sensors. Whereas if you have loggers with radio at the position of the borehole, then you're not crossing equipotential lines with your cables. In that case, the installations are very robust against lightning. So installing loggers with radio communications between the collar of the hole to the gateway, not only at the end is it less expensive than long cable lengths that you have to put in trenches, but on top of that, you're inherently protecting against lightning. And thank you very much.
Thank you, Pierre. So now we've got a panel starting to get into the system design. So Ankiel, Leandro, Manuel, Rowan, and Pierre, you're on the panel, and Edgar will be chairing it. So we might try and cut 5 minutes off if we can. Well, there's two different sections. We've got 30 minutes for each one. All right?
Yeah, pretty much.
Yeah. Yes, we'll have lunch after. You're sharing both.
Yeah, we're checking.
Yeah.
It's just one here.
Yeah. So we had 40, but if you get to 30, be good.
All right, here we go. The idea of this session will be to discuss typical problems and issues that we have when installing instrumentation. Then one, in my opinion, that is really common, and I'm just going to put it here for the panel to discuss, is the installation of vibrating wire piezometers. I don't know if you know, then they have a filter right in the tip. Most of the people decide to grab this filter and put it in the bin and replace that with silicone or other stuff to basically sort of a hurry up the installation. Then I would like to basically start with that topic, Pierre, if you don't mind, and what is your opinion in leaving the filter, removing the filter on BWPs during installation?
Okay.
There's a microphone in there for you.
Yeah. Actually, I heard about that practice only yesterday when you told me of getting rid of the expensive little filter that we sell.
I think no, on the
No, it's not
microphone.
expensive.
Yeah, you know.
It's only-
That's it.
Yeah. And removing the filter, I mean, just the top portion, and put grease behind. Any method, in my opinion, in the end, doesn't change too much, in the sense that water is hydrostatic, grease is hydrostatic. So when we put a piezometer in the grout cures, and it's permeable. We said that the permeability is low, 10⁻⁶ centimeter per second, but the water flows through the grout, makes its way to the filter. If there's a filter, it goes through that, and then gets against the grease, and which is also hydrostatic, and then it converts into a pressure. Actually, there is a very recent article from a consultant in the US who tested what we're just saying. Does it make a difference if you put the piezometer tip up or tip down? That's another story. Should the piezometer be tip up or tip down? Their conclusion is, don't worry, it changes nothing because they've tested both situations in parallel. And same thing for saturation of the piezo also. Yes, it's a good thing to saturate the piezo, but if you don't saturate, air will dissolve into the water very rapidly, and air is also hydrostatic transfer. So more or less irrelevant, all that.
Conclusion.
More or less, but do it right. I mean, follow the instruction of the manufacturer. That means still do it right, saturate but at the end of the day, it changes nothing.
Okay, thanks for that. Have another question. In this instance, going to go to Rohan. When drilling through rock field to install shape arrays, what sort of the challenges are the most common, and the ways how you have found ways to solve those problems? You have basically is a lot of experience in there drilling through rock field, big boulders and mine ways to install shape arrays, and yeah, we like basically your experience and lessons learned from that exercise.
Yeah, for sure. It is obviously very, very difficult drilling through very coarse, broken ground or waste. In our experience, we've got particles up to 3 meters in size. Recently placed fill is not necessarily fully compacted yet, so you will have, when the drillers pull out to change a drill bit, they'll have the hole will just collapse, or they'll have rocks will actually roll in the hole, so that you end up doing a lot of re-drilling. So that just comes down to how you plan and cost the program. You have to put a lot of fat on your schedule and your budget. You have to do, as we mentioned yesterday, you really need to do double tube, so you have to case the whole way, and don't progress your drilling head too far past your casing. So you drill 3 meters, advance your casing 3 meters, and just keep doing that. It was incredibly slow, especially if you're going through hard rock. But you just have to wear it, otherwise you risk bending the hole and start all over again. You need to go a larger diameter than you expect. So for a shape array, if you're installing an 85 mil casing, when we were drilling, we would typically do a PWT hole, which is 160 mil PWT. That's to allow for you will have some falling, and to allow enough room between the casing, the shape array casing, the drill casing, and the drill string itself, so that you don't get bound up, because you do end up getting a lot of rocks that get caught in between the drill bit and the casing, and again you get jammed up, so you have to pull it out. And you want to avoid pulling that as much as possible. So if you can, on a short hole, say 30 meters, if you can do the entire hole in a single pass without having to pull the casing out to change the shoe, then you really need to try and do that. So stress the drillers to manage their shoe wear, because the minute they pull that casing out of the ground, they're basically starting again.
And with the extraction, how to extract them.
Yeah, and so we would do triple tube to extract the core. Through the fill, you don't really get any sample that's worthwhile having. But you can, if you've got a good understanding of where the foundation is, you can slowly write down, they can turn their water off, and you can actually get a pretty good sample from that foundation contact, and then keep sampling into the foundation. One thing I wanted to mention about the actual installation grouting of the shape array casing was, in a loose rock fill, if you use that typical grout method, you can pump cubes of grout down and you'll never fill it up, because all you're doing is grouting the entire embankment.
You're reinforcing the rock fill by injecting grout, yeah?
Yeah, so for example, we put 7 cubes down a single drill hole, and when we did the grout, it hadn't even come up 10 centimeters.
And how you manage to basically backfill fill that gap in between the chamber array casing and this massive rock fill? I mean, what is based on your experience, what was the solution?
Yeah, so we would work with the designer, and we came up with a different grout mix that once set would have the same consistency and strength and porosity permeability as the more liquid grout mix, but when it was actually pumping down the hole, it was more like toothpaste. So you can't just use a normal Fremy pump, you have to get a monopump to pump it down, and you have to do quite small lifts because it's got quite high buoyancy. And then you'll do a 5 meter lift, let it set, and that then holds the casing down and do another 5 meter lift. And that method of having a really thick grout seemed to work. It didn't just disappear in the fill. We've also used granular backfill in cases where we just can't get the grouts. We use granular backfill only in the rock fill section. In the foundation, we've always used the granular backfill seems to work quite well.
Excellent, thanks for that. Leandro,
If I can add,
yeah, go ahead.
if I can add something there, is don't forget for situations like waste dumps and situations where possibly you expect rather large displacements, that worst case, if your routing was not correct, there were some areas that were not routed around the casing and so on, that the maximum displacement that could result from that you would appear on your graphs and so on is maybe an annulus of 1 or 2 centimeters. So that means that you may have a noise of 1 or 2 centimeters in your inclinal profile. So that one that there is less repeatability than the 2 millimeter per 30 meter that I was mentioning yesterday. But in the big picture, it cannot be more than that. So anything that exceeds that noise of 1 or 2 centimeters is real displacement.
Okay.
If you secure it at the collar, yes, it can move inside, but there's a good chance that by self-weight and so on, the whole casing has wedged itself a little bit in there, and it's in reality not going to work that much.
Thank you for that, Pierre. Leandro, installing BWPs, what for you is the key elements to look after, or QA, the quality control and the quality assurance? Because typically the most common mistake is you install a piso, you lose the calibration file, you don't have a good record of the instrument that you installed. What is your experience? What are the key elements that an operator or a designer needs to maintain, keep, and why?
Yeah, I think it's a very interesting point because we are working in an environment that's the ongoing construction. Pretty much currently we have 980 BWPs in operational BWPs, and that's basically 2 embankments with 2,000 meters or 1 kilometer each. So it's very hard to keep all these BWPs functional. And the challenge we have during installation of the BWPs, as you mentioned, is to keep the records of the calibration sheet. But the way that we are drilling these BWPs allow us to have more control because we have a dedicated team to follow these installation and to logging the board holes. So we have quality control, QA/QC during the drilling, that's logging the board holes, and during the installation, we have a procedure that we need to follow. We have all the calibration sheets. When you don't have, sometimes happen, we have the information from the BWP, so we can get this information from the provider, for the vendor. So in terms of QA/QC, you don't have too much issue. Sometimes you need to be careful with the first reading. That's someone mentioned yesterday. We need to zero, and saturate the BWP prior to the installation. I think that's the key message you have from our teams in the Valley.
Excellent. Manuel, just moving a little bit more towards actually designing your monitoring system. How we do that? How we basically now, we've been through to almost 2 days of looking into failure modes, instrumentations, all these fantastic tools that we have now. Now, as the designer or engineer of record of a site, you need to basically design it. You need to tell the owner of the asset, I want all these instruments. How you do that and why? Or what is your thinking process? How you will get to, I need these instruments. I need 100 or just 10 or 50. How you make that call?
So from the design perspective, every site, every facility is different. Instruments are usually, so the traditional instrumentation is discrete, so it's a point in the dam body and the foundation. In the case of inclinometers, well, yeah, it can be then a line. So, but in essence, 1D. That's with traditional instrumentation. But I would say it's important to be open-minded and combine. So redundancy and really combining different technologies is a very powerful tool. And to decide where to install the instrumentation and the number, you always need to read the room, account for the resources the client may have, so that you don't overdo it, because it's better, whatever you do, make sure it's well done. You have the team fully invested, and you have the proper people to do the installation and the proper people to do the supervision of the installation. Now, for the design, I would really look at what we have in the foundation. So if we have a large, so the crest length of a dam, of a TSF, we have kilometers. I would try to break it down. What do we have in the foundation? Do we have any faults? Do we have any changes? So that's a number one thing, to try to break it down into sections or areas or walls, or maybe with a typical water dam, you're always going to have a fault in the middle of the river. So maybe the left abutment, the right abutment, the central area. So always look for that to break it down, and then focus on the failure modes in each one of those areas of your structure. And then once you have the failure modes, ask yourself, what do I want to know here? Do I want to know where the phreatic surface is located? Right. So what can I do to know about that? Piezometer? Okay. One piezometer, several in one vertical, and that's how you break it down and you decide where to place them. And you try and combine to have some redundancy. If the dam, the foundation is very, very critical, if you think the materials are not going to be that homogeneous, then try and have sections every number of meters, and try to have some redundancy. Maybe you're going to combine discrete sensors with these new technologies, with geophysical and INSAR, and that's really going to give you a good picture. But always driven by failure modes and what you really have in the foundation and in the dam body. And on top of that, all the environment. So it's always good to make sure in the procurement. So sorry for bring this up, but it's so important. It is so important. If you're a dam owner, if you're a ministry, the procurement, what you include in the terms of reference in the specifications, it's not just the technical features of the devices, of the sensors. Obviously, the range is a big thing, and the type of let's say cables and sensors you're going to use, who is manufacturing that. but also account for the installation. You want to have as well, like an office and some place where you can store the instruments when you get them on site. So you can actually check out all the references for each one of the instruments, all those calibration forms, the zero readings, all that needs to be written down and recorded. So you really need to have a team of people taking care of that and have a proper storage of the material and then obviously supervise, take pictures, account for anything during the installation. And that should be really part of the design. So the design is not just the drawings and a few technical, but you really need to include, think of the procurement, think of the references for the people who are going to do the installation. Think of the references of the even the manufacturer. So have you dealt with this type of foundation? Have you with this type of dam? That really makes a big difference.
Okay, then if I got this right, the message is you divide a 5 kilometers dam into sections, and you're trying to understand if the sections are the same or they are different, and that is the way how you target your instrumentation.
Absolutely.
And then you think about the person that is going to install. You are the designer, and then you advise your client, we need to install this. This is the technique, and you tell and you advise how you want to keep the records. Is that right?
And even how that is going to be operated in the future, and if there's going to be proper operation and maintenance, so proper OMS. Because if you don't really trust that dam owner is really going to take care of that, if there's going to be a lot of turnover in the personnel, the professionals that are going to be doing the readings and taking care and interpreting the data, then you have to go for very conservative, very robust designs. So make sure you have redundancy, make sure that, everything is perfect and it's going to be very sturdy and really withstand the passage of time and people. And if possible, in the terms of reference and the procurement, apart from all these details and how to install it, how to do how you receive the materials, quality control and assurance, during all that process, also include training. So training of the people, and regular training if you have a lot of turnover. Tailings facilities just go on for decades. So that has to be really part of that dam surveillance program we talked about yesterday. So that is a big thing. Or if it's a big project that it's going to be going on for several years, same thing.
Thank you.
Can I just quickly add?
Yeah, sure.
I'll just add to that, and it's probably just part of the design, but less on the designer side, more on the client side, is when you get a design, you need to look at how you're going to integrate. So if you've got a brownfield system, you need to look at how you're going to integrate these new instruments into the existing system and assess any flow-on effects that you could have. If you're plugging in your radar in, you could completely overload the system with the amount of data that radar is going to be generating, and you could be up for a huge bill to upgrade your servers or upgrade your comms network because you may already be in capacity. So that integration piece is very, very important, and the designer often can't do that because you don't have access to the information.
And that is just a nice introduction for the next stage. Is we talk about installation, design, and I want to have your comments about data management. Where we went through, we installed the instrument, we designed the instrument, we installed the instruments. Now we need to manage all the data, and we need to connect all this data to a system that might not exist, or it might be evolving, or we are in the middle of the jungle, or somewhere in PNG, and where you don't have Wi-Fi. Then how we manage that data? How do you see that happening? How we keep those records? What is your experience on that?
Yeah, no, it's not a easy task, right? It's a daunting task. I think we also have to remember that this is a sort of chain of events where you have to get every single thing right. You have to do your PFMA, you have to design the system, you have to buy the system, it needs to be installed. You need to collect the data, you need to interpret the data. And it's not really until you get to the interpretation part that you know if all these previous ones have actually worked or not. Right? So it is something that should be in the thought process already when you're starting up thinking about your system. Another thing is that you sort of need to try to future-proof it. No system lasts forever. Right? So when we're designing these, we need to think about do we need to upgrade these systems later on? Like you mentioned, do we add in additional sensors later on? Is our bandwidth sufficient? Is our sensors or is our logging equipment up to the task? How are we going to get these data from the site to some cloud server somewhere where we're going to interpret it? Do we do the interpretation at the servers on site, or do we do it in the cloud? All these things are very important questions in design. But I do think technology is helping us here. We're now using, just like standard network cables to connect a lot of these sensors. We're moving away from the copper cables. That works great in some instances. We can have fiber optic conventional sensors where you connect them using fiber optic cables. You avoid some of these issues with lightning and other things. So we are getting more and more tools to help us, but at the same time, just the complexity of having more data, having continuous spatial data, needs a whole other level of system to actually manage these things. The days where we could plug this into an Excel sheet and you have an engineer that keeps track of this over time is just gone. You need some type of system to actually that someone can come into. You can train a new person, and it's not linked to a specific that one key resource that you can put in all this manually. And there needs to be more on an institutional level where you have these type of systems.
Excellent. Thank you for that. I want to open the floor for the audience, and I want to see if there's any questions. Yes, great. We have a few. Somebody can help me with the microphone. Answer the microphone.
Just 1 second.
Yeah.
While we get the mic to the just going back to what Arjun just mentioned, forget about the spreadsheets. Okay, just forget about spreadsheets. There's no way you can get away with spreadsheets anymore. And there's no way you can keep track of all the constants, the formula with spreadsheets. You really need a proper database to include not just the raw data, but all these metadata. So coordinates of the sensor, all the formula, all the constants, all of that needs to be installed. And
I was that way.
Here's the mic.
Yeah. Keep going. Let me just. Yeah.
Well, then, and combining that with these surveys we've talked about, you really need cloud systems and really plan how you're going to analyze your data, the type of plots, setting up the plots is very time consuming and needs to be planned and carried out by a proper team. So all of that for the data interpretation is a really big thing.
Okay, then we start with the questions over there.
So myself, I am Giri. I'm looking after the geotech function as our group of mines from the Sunzen. So my question is, for the piezometers nowadays, the vibrating piezometer comes with the thermistors. So how important it is to have that range well defined when you are preparing for the specs?
Yeah, you want to?
Yeah. All vibrating what? I'll pretend it's a microphone. It's not working.
No, it run out of battery.
So vibrating wire instruments nowadays comes with a thermistor because it's very easy to put a thermistor inside, and it's a useful information of the temperature. In dams and storage facilities, thermistor is a measure of pressure that can be useful also to help assess about about seepage and seepage flows and changes with season and so on. If you have many piezometers in the tailings dam, that temperature and formation can be interpreted very favorably. And it comes basically free of charge for you. So you're asking how to specify it. Well, your vibrating wire instrument should add a thermistor with a repeatability of map. What do I say? Repeatability of 0.5 degrees C or 0.1 degrees C. You should,
Yes, yes, and yes. And
You can grab the microphone now. It's working now. Yeah.
yeah.
it's working.
The VWC to be working. Is that correct?
But, yeah, that's correct. But importantly, you don't need you don't need a thermistor for the VWP to work. So yeah, sometimes people are concerned because the thermistor for some reason has stopped to work. They're concerned that the piezometer is not functional anymore. That's not true. It is still very functional. As I said, it's still a bit a free of charge thing that we put in there. It's so easy to store it.
But it's true that depending on the location of the piezometer, if it's very close to the surface, or maybe if you have it downstream, because you want to know how the water is flowing, and how so the energy of the water flowing is dissipating towards the downstream area. Then you want to do the correction properly. Otherwise, depending on the type of piezometer and when it was installed, you may have some funny. But generally, of course, if the piezometer is in the foundation, that's not a big issue. But if you have the measurements of the temperature, and notably in the foundation, it's incredibly useful because you can really detect seepage, analyzing the temperature and the evolution of the temperature in those piezometers. So I've used that many times, and when you see that, that's when you can resort to maybe geophysical, ERT, and really confirm that. So really use that data. If it's available, it's free of charge.
Okay, we have Michael.
Can I add a small thing on the therm? So it's true that we forget.
We have a lot of questions, and I would like to go through as many as we can. Sorry.
My question to you, myself, Mahendra Singh Rathore from Hindustan Zinc Debari. Just want to know for the existing TSF facility, can we have an IPI or shape error in the angular? Means in the slope, parallel to the slope, or in the angular form, we can install that IPI or shape error. So it will not damage the existing geosynthetic liner or in the slope. Can we install in angular?
Well, it's to be studied for each individual case, but the big picture answer is yes. Inclinometers and shape arrays can be installed in inclined fashion. So that's your question. Now you want to add it parallel to
parallel to the slope.
To the slope, to the liner. In the big picture, the answer is yes. In practice, there might be peculiarities, but in the big picture, the answer is yes.
Anywhere it is installed, have you seen?
Oh, yes. We have cases of inclined installations. Yeah. Other people do it. That's correct.
Thank you.
We have one here, I think.
I have just one question for all. Please.
No, it's just probably close to. Try again.
Okay.
No, it's something there. Okay, no microphone.
Well, how to repair the cyclometer? We're talking about installation, but how to repair? I give example. After 1, 2, 5 years after, they usually give you temperature, but not pressure. 1 week you come see there is a pressure, not temperature, or sometimes negative product. Find
Is it? Yeah. Is it a vibrating wire piezometer?
Yes.
Okay. Is it read with a portable readout or a data logger?
Yes. You see exactly.
A portable readout.
Portable.
It's a portable readout. Okay. Yeah. Is Brent Randall here? He will be talking about that.
We'll be joining after lunch.
He will be here after lunch, yeah.
Okay.
So vibrating wire piezometer can be diagnosed, not only read with a cortical readout, but there are also devices that are called vibrating wire analyzers, which are a little bit like oscilloscopes, if you will. But the objective is to evaluate how strong is the vibrating wire signal, because in your case, it appears that sometimes you have a reading, sometimes you don't have a reading. If you don't have a reading at all, that's another story. But in your case, it appears that sometimes you have a reading, sometimes you don't have a reading. So it appears that the signal is low, it is not strong. So the reason for that then has to be evaluated in the field in reality. But among others, with the vibrating wire analyzer, it will depend on the length of the cable also. So the electrical resistance of the cable will be useful information to understand on whether it's a very long cable or a short cable. The piezometer had been affected by lightning. The story that I was showing a little bit earlier, it's possible that the piezometer has been affected by lightning. It depends also on how old the piezometer is, what manufacturer as well. It might have an incidence.
I would like to.
Just keep in mind that we have
Just 30 seconds.
30 seconds.
I would like to add one big thing. I've dealt with bad data from piezometers, and sometimes as well so how the cable goes into the piezometer can be an issue. So if you don't choose the proper piezometer or it was not properly manufactured, that's one thing. So choosing the right piezometer, so that the cable, the isolation, and that sealing is correct. And even inside of the piezometer, I've always come across piezometers that were not properly manufactured, and there was actually a mechanical just plan because of not being properly manufactured. So all of those things, how it was installed.
We have time for one more question, and that's it. I let you. No, Malcolm. Malcolm can ask question.
In embankment dams, having chimney and a blanket filter, if we are providing piezos, what should be the bottom level of the piezo? It should touch the blanket filter if we are providing in the downstream side to observe the ferritic surface, or it should be above the this blanket filter level?
Question for the designer.
So watch out for inverted filters. If it's so do not use crushed limestone, because crushed limestone eventually will be cemented and you will have a poor pressure buildup. So even though an inverted filters should be draining and you should have zero full pressures, watch out. You want to install, I usually install piezometers at the toe of the dam and downstream of the dam, and even in the inverted filter as a traffic light. It should be zero, but you may end up, most of the time you have full pressure. And you want to know how the energy is really being dissipated from upstream to downstream. So also keep in mind the elevation. If you use the same elevation for sets of piezometers, you're going to be able to have a plan view with lines with the same piezometric water. That's incredibly useful to know exactly what the water's doing. And if at the toe, you've got this vertical where you have several piezometers in the same vertical line and properly installed, you're going to know the exit gradient. And so if you have different layers in the foundation, that is also very valuable. So, but yeah, I would install in the foundation contacts between different materials. So one in one material, another one in another one, in the other formation layer or material within the dam body. And in the downstream shoulder, always piezometers in the inverted filter, apart if you have a core or impervious material, obviously. And if you have a grout curtain, upstream and downstream, pairs of piezometers, different elevations. And then, of course, you need to go into the nitty gritty of whether you do it fully grouted or you have an area where you have 2 or 3, holes. And so it really depends on the foundation conditions. But that's going to give you really the picture of what the water's doing and if you have proper dissipation and gradients for internal erosion and in between the materials.
Okay, we run out of time, I think. David, is that right? Yeah. Thank you to all the panelists. Yeah.
I don't have it.
Yeah. No. Come. Oh. Okay. I'll have all the panelists up here quickly to get. No, forget about it. So we're next going to look at how to actually acquire the data, and so we've got another panel with Mohit Bhutani from Canary and Chris Fagan from Sept2024. So hopefully you're here. Come up.
Presentations, right?
Yes.
Yeah.
Do you have by any chance in a USB? Because
No.
I have a problem. No, it just crashes.
Oh, okay.
Yeah.
I can put it on the USB.
Yeah, if you don't mind. I think I have the.
I put it on the quite close. I know. No, it's not. It drives.
Can I?
We've got a I can put it on a USB. Yeah, you can. I can't use the USB.
Yeah, okay.
Just what happened this computer.
Yeah, just.
So we just while we're waiting for short delay here while we get the presentations organised, you can go back to your. Now you've heard about design, you can go back to your exercise and do your design. And if anyone needs their a spare copy of that sheet, I've got some up here. So if you haven't got the A3 sheet of your exercise, put your hand up and I'll get you a new copy. Because don't forget, there's this piezometer for the prize winner of the best design. So it is pretty good prize.
Oh, so going to send you a bill.
Oh, it's in the hotel. All right, so a few more sheets here.
All right. This computer is we are ready to go. So guys, yes. David, you want to?
Yep.
It was really short name. Sorry, didn't have time to. We're gonna start now.
Yeah.
You can.
You're in a sheet. You're going to introduce Mohit?
Yeah. No, you have a.
Oh, yes. Okay, all right. Well, I'd like to introduce Mohit Bhutani. Mohit is a mining project engineer with more than 5 years' experience in technical and strategic consulting for project management, with a demonstrated history of working in the mining operations and management sector. And his skills include drill hole analysis, bench composting, block modeling, pit expansion, and a lot of other analysis systems. So over to you, Mohit.
Thanks for the introduction, David. Yeah, first of all, I'd like to start with thanking all of you and the committee to organize this session. It has been a really good session with a lot of interesting discussions, a lot of interesting topics. And I love the fact how these sessions were organized and put together in a way that it flows together as a story. We already talked about a lot of monitoring instruments, what different types of instruments we have on the tailings dams nowadays, the different types of technologies, what could go wrong with the technologies, and what are the challenges that we're facing with consolidating all the data into a single place. And it just happened to be that in just the previous panel discussion, it was discussed, and Manuel really put it very nicely, that we need to get away from spreadsheet culture, because with the amount of data that we are ingesting and having nowadays, that it really gets difficult to sort of analyze everything using spreadsheets. So my presentation perfectly segues into the next portion of it, and basically how to integrate the data, how to analyze it, and how to put everything together at your fingertips. The basic agenda for today's session would be how data was collected, how it's managed, how it's kept secured, and how it's basically used. So as you can see, we have a lot of data. We have, with increasing technology, we are no more collecting data manually with at all the individual locations. So we have the data collection, but that data collection is now mostly automated. Then we need to import the data. We need to store the data somewhere where it's safe, and we have to keep it redundant so that if things change, if things roll over, we have redundancy to portion the data again. And the major challenge is data processing and the data output, which comes into play for data interpretation. The 5 V's of big data. Like I said, we have so much data coming in, like it's no longer qualified as just data, it is big data. So we have volume, velocity. So volume is the quantity of data, velocity, the rate of accumulation, if it's hourly, daily, every 12 hours. Veracity is the accuracy of the data. We'll get into more of each of these in the next presentation. Then the variety, like many sources. Again, it was discussed in the previous panel discussion that we need to have redundancy, not just with the data that we already have, but also with the different types of instruments that we integrate within the same area. So we have redundancy in different instrument types as well. And viewing, that is the accessibility part of the whole chapter. So data collection, it may seem very straightforward, but there are a lot of challenges when it comes to collecting the data in terms of how it's collected, when it's collected, how the data is transmitted, how it's stored, and how it's transferred over for final analysis and computing. But basically, we need all of this data to make its way to the end user, and end user needs to have direct access to all these types of data as well. This is not going to waste too much time into explaining what this is, but it's basically a lot. Like I said, there's a lot that goes on with collecting the data at source and transmitting data over for the final analysis. So we have the direct wire connection data, which basically is transmitted directly through the cables onto the servers, storage facilities. We have Wi-Fi, we have cellular models, we have radio connection, and we have satellite connections. So all of this data flows in, that's all collected into MinePed, needs to be transferred to a different media converter or servers to store the data and transmit all the data to the end user access. We discussed a lot of these instruments in the previous sessions, which are different instrument types for different types of analysis that we need. So we have we have instruments and we have data for ground movement. We have instruments and data to measure pore pressure and water elevation and heat and all that. So we basically can categorize each of these into different fragments in the data collection market. And the biggest challenge that we face with that is each fragment has its own challenges in terms of interpretation and in terms of conversions. So what we need here is a final solution to basically move away from the market fragmentation and move it more towards market integration, or you can say data integration. So you have all of these different fragments of the data that we collect, but each of these different fragments have their own unique platforms to view the data, to analyze it, and to create reports to visualize and all that. A major time saver and an effort would be to simply just translate all of this data into a single platform where you can basically overlay all the data on top of each other, which are already georeferenced to the locations. So for example, if you have radar data, the geo-radar data, you have INSAR data, you have prisms for a single location at a mine or a tailings dam. So you can analyze each of them separately in their separate softwares, whereas, or you can pull the data out, migrate it to an Excel sheet and analyze it there and then compare them together. But what if you could do that all in a single place? What if you could do that in a single platform and all the data is right there at your fingertips to access and analyze? So that's what data integration will help you with. Yeah, like I said in the previous slides, there's a lot of moving parts. So we jokingly compare different vendors as herding different many cats together. Yeah, so data management. We have, with this growing technologies, we are collecting more and more data. It's not just in kilobytes or megabytes anymore. It is going towards the terabyte territory. So we need a better way to organize, sort, and manage the data that we collect. So there are different softwares or programs that we can use for an advantage. So what is data basically? Data is numbers. The numbers that are stored in rows and columns, which is basically a table and a database. A set of tables is a database. So we have the database softwares, Firebird, Postgres, Oracle, just the usual, that we can use at our advantage for that. Of course, database management comes with its own benefits. Like I said, it's organized data storage with time series data. So you can go back in time, compare the whole old data with the new one. You can do easy mass operations. You can easily connect one table with another to create relationships, generate calculations, and make more sense of for example, more sense of a frequency data, convert it to a water elevation data or pore pressure data automatically by just creating relationships between. You can automate querying, you can automate reporting. A lot of the sites have monthly reports, quarterly reports, daily reports that you need to analyze the data or keep a check. So with real-time data ingestion and data output, you can easily simplify your reporting process. And since we are already using a database softwares, we can easily scale the model to accommodate any number of data points or on a larger scale. Again, it basically that streamlines the data management process, making it easier for organizations to make more informed decisions based on more accurate data. Since now we are moving from storing data into logbooks and papers, now we are storing data on digital platforms. We have an insecurity about data security. So there are countless ways that your company's IT team will be able to help with the data security, which could involve deploying physical servers, managing multiple firewalls, data encryption, restricting user access, and all that. But yeah, there are multiple ways in the IT domain to do that. Yeah. This is a basic IT infrastructure example where you have the instruments and the data loggers at one level. This is the Purdue model that a lot of companies nowadays use. Transmit the data to servers. The servers move up, process the data, and provide it for an end user to analyze. How data is used, it's basically you have a lot of different information sources, a lot of instrument data. You integrate the data, you validate it, you evaluate the data to generate models, and you basically make your decision based on that. And why do we need data validation? With so much automation that has come up nowadays, it was mentioned a while ago that sometimes the instruments don't report properly. Sometimes they have invalid data that flows in. And since it's an automatic process where the data is being collected every hour, you need to also make sure the data is consistent with what it's supposed to be. For example, if you can create thresholds that will automatically invalidate the data that came in incorrectly, and it will not affect your charts, it will not affect your plots and your calculations. So it reduces a lot of errors, it makes the data more consistent, and enhances decision making and saves a lot of time. Evaluating data, it's basically you have to combine multiple data sources. You can combine them into a single plot and identify trends, manage risk, and do more detailed analysis by comparing multiple data sources into a single platform. This is the basic decision-making process, which involves identifying the potential risks. Oh, sorry. Yeah, so identifies this potential risks, analyze the risk, evaluate predictions, treat to eliminate the risk, and continue monitoring. So monitoring will always be there, and decision making will always be a part of it. This is where the monitoring plays a role in the risk management process, where it helps implement and safeguard those thresholds, and it reduces your risk factor to tolerances. We also have the principle number 7, as it was mentioned earlier, the principle 7 for the GISTM, where performance monitoring program, engineering monitoring system, then establish specific objectives, analyze, and report the results. Thank you.
Thank you, everyone.
Take a seat. Right, so thank you, Mohit. Now introduce Chris Fagan from Sixth Sense. Chris has got 18 years experience in delivering geotechnical and structural projects in Australia and abroad. He's been to many interesting places, including now, although you might have been there already, I don't know. And his career has covered a breadth of roles from site engineer to project manager, and he's now responsible for the broader operations of Sixth Sense within the Oceania territory. So should be good. Thanks, Chris.
Okay, thank you for that introduction, David. I'm not going to spend much time talking about Sixth Sense, but we will be exhibiting at booth 61 during the conference. So if anyone is interested, please come and have a chat to me. So a quick agenda. I'll talk about why we might integrate monitoring and inspections, in particular why we might do this in a real-time fashion. I'll then look at what are some of the key features of an integrated monitoring and inspection system. I'll look briefly at a couple of case studies, and then I'll make some conclusions and recommendations. So why might we integrate monitoring and inspections? We've talked a lot about this through the last couple of days, so I'm not going to go through all these points. But from my perspective, the key is really to de-silo all of that data. We see we're collecting huge amounts of data whether that's monitoring data or inspection data. It could be geotechnical information, it could be INSAR data, it could be survey data. The aim of an integrated monitoring solution is to de-silo it. It's to get it so we can see all that information together and we can access it easily. In the end, that's going to make communication of alarm exceedances in case of any emerging issues much easier, and it's going to help us support, or it's going to help the operators then support the decisions. Okay, they're spending time making decisions, not gathering the data. It'll help us to comply with our relevant ICOLD or ANCOLD guidelines, and it'll help us develop a common and efficient situational awareness. So what do I mean when I say situational awareness? Let's look at the situational awareness maturity model. It goes from low situational awareness at the bottom up to common and efficient. So at a low situational awareness on site, the site data is inconsistent. We might not be collecting all the data that we need, and that data is stored in different places and people aren't communicating. We move up one level, we get diverse, okay? So we might be collecting the data, but it's stored in different places, and different individuals have control of those different data sets. Moving up one more, we get to costly. Okay, so data is gathered in one place, which is great. So we do have that common situational awareness, but it might take a lot of effort to get there. So you're spending a lot of money getting all that information into one place. And at the top, we've got common and efficient situational awareness. This is really the aim. This is where we want to be. All parties have a common understanding of the site and the data, and resources are spent on solving issues and making decisions. Resources aren't spent on collecting the data, integrating it. The data's there. It's available for you to then make decisions. That's where we want to be. So how do we do that? Well, a good start is to have all that data in one place. So that can be your geotechnical sensors, your in-ground sensors. We've talked a lot about these, inclinometers, piezometers, and so forth. Your above ground structural and deformation sensors, manual and automated survey, INSAR, LiDAR, different types of sensors, all your environmental data, and then also your visual inspections, so your regular surveillance and your ad hoc surveillance. You've seen a presentation from Canary that does a similar system. Ours is called Beyond Monitoring. It's that integrated monitoring system that brings all that data into a central place. Some of the key features of an integrated system are, of course, data integration. Apologies, it's a bit hard to read that text. So bringing all that data into one place. Being able to correlate and do your data reduction. So calculating your engineering units from your raw data and cross-correlating between different types of data, different systems, different sensors. A good start is to be based on a GIS layer-based platform. So using a layer-based system enables us to compute or visualize large amounts of data sets efficiently. Of course, it should include a robust alarm management system, should have integrated reporting, so you're able to disseminate that information efficiently out to all the relevant stakeholders. Should also include some form of journal, and we've talked a bit about that, where we need more than just the measurement data. We need the commentary around the sensors. We need to know if there's certain phenomena, certain things happening on our data. We need to be able to track and record why that might be. So having a journal to track that information against your sensors is important. And of course, being able to manage your visual inspections in the same system is very powerful. You can then correlate between your visual inspections and your sensor data. And also having a vendor that respects the data security and the data integrity. This is becoming much more important where solutions are cloud and SaaS hosted. We can also improve the efficiency by using real-time data collection. There's many different real-time data logging solutions out there on the market, and it really depends on your site, the size of your site, whether it's above ground, whether it's below ground, whether you've got mobile, 4G, 5G communications, whether it's satellite, whether it's Wi-Fi. There's a lot of different solutions on the market there that you can choose from. But in the last 10 years, they've got a lot cheaper and a lot easier to deploy. There's also, of course, satellite-based technologies, not necessarily real-time, but remote sensing, things like INSAR, GPS. We can also look at things like surface water changes using satellite-based technology as well. So consider all these technical advancements. These can help ensure data availability. So they can help ensure that when you need the data, it's there. Yeah, that's lost. Okay, and they can help reduce your operational expenditure over time. We talked quite a bit about INSAR, so I'm not going to go over INSAR again, but the important thing to note here is make sure that you're choosing an integrated monitoring solution that can handle INSAR and point cloud data as well. And just a note on the dual orbit INSAR data, also consider this for your particular scenario, but also consider the limitations that we can only look at east-west movement in a horizontal sense. So check how your structures are aligned and how you want to monitor that horizontal movement if you're using INSAR. So visual inspection, of course, is an important thing. And if we can integrate this with our monitoring sensor data, then it just makes that data even more powerful. So some of the features will be of such a platform will be that you can define your visual inspections, you can schedule them easily, you can push them out to using mobile phone applications, you can push those inspections out to the relevant users. They can then report and monitor the evolution of the structures with alarm triggering and automated reporting. Benefits, of course, can be standardization of your inspection procedures across an organization. With that, you'll get some productivity improvements, and you can also get validation and cross-correlation with your monitoring sensors. At the end of the day, this is helping to de-silo all that information. Of course, alarm management is important. Alarms are commonly sent out by SMS or email or mobile phone, also with push notifications. So it's important that your sensors can alarm efficiently through your integrated monitoring solution. And it's also important that you look at your system alarms. So if you expect to get data every day or every hour or every 6 hours, make sure you set up those system alarms. So if you don't receive the data when you expect it, you'll be informed. And reporting. It can take a long time to put together reports, particularly if those are daily or weekly. So having an automated reporting system that can push them out to the relevant stakeholders is important. I'll look at a case study of a few different sites just briefly. This is a small tailings facility in Queensland where we are monitoring the pore pressure with piezometers. It's small, but it's state of the art. Everything is wireless, it's solar powered, all the communication is remote. The alarming and the reporting is all automatic and produced within the system. And you can see the phreatic surface on your dashboard of your tailings facility. Next is a water dam. This is again in Australia where we're integrating both old systems and new systems. So we're deploying wireless radio networks with piezometers along a 7-kilometre embankment there. So using a mesh-based radio system that will hop that signal along the embankment. We're also automating the older systems, the hydraulic piezometers that you see down on the bottom right-hand side, so that the dam operator doesn't have to go and visually sight those gauges every week or however often they need to check those. And this is a large TSF site integrated or coupled with a couple of mines. At this site, it's hard to read those numbers, but there are over 1,200 prisms monitoring targets being read automatically by a network of 12 total stations. I believe they're provided by Hexagon. And there are about 1,300 piezometers, all wirelessly connected through a world sensing data logging network. All of that data is feeding into Beyond Monitoring. In the middle, you see an image of that tailings embankment. It's hard to see the arrows, but there's arrows indicating the direction in which those prisms are moving. And we've also got a heat map, a contour plot in the background, which draws your eyes to the area of that embankment that is moving. Down the bottom, you see some INSAR data. I believe that's being provided by Trey on that embankment. And just drawing a cross section through the embankment, you can see it's really moving. And on the right-hand side, we've got inclinometers, and there are additional sensors. So there's a huge volume of data being collected at this mine, and all visualized and processed in an easy to interpret way for the operators to understand. Yep, sure. And of course, consider a solution that might be fit for purpose for your enterprise. So many operators have multiple sites, so consider a solution that can handle all that data and have all your sites in the one solution. So to conclude, one size really doesn't fit all when we talk about systems integration. Okay, so carefully consider your specifications if you're looking for a system, and consider the wide range of instrumentation available. Some have benefits and limitations. Speak to your vendors; they'll be able to advise you. Carefully select the integrated monitoring platform. So it should be holistic. It should be able to ingest data from any type of sensor and system. It should de-silo the information. So it needs to bring it all into one place where you can cross-correlate. Of course, cybersecurity is important. And again, consider the suitability for deployment at an enterprise level. We've seen this mentioned a few times. Don't underestimate the data management. This is really the key to data quality. Okay, we don't just install a monitoring system and forget about it. We've got to look at the data. We've got to watch the data. We've got to ensure it's quality controlled. And don't forget, at the end of the day, data availability and data quality are really critical. So what does that mean is when I want the data, it's there. And when I look at that data, I know it's been quality controlled and it's actionable. I can make decisions on that data. Thank you.
We have a small panel discussion, and I want to basically start looking at the two presentations. It's quite overwhelming, and I'm pretty sure that a lot of you as owners and of the asset is all these data. It's just data management, cloud-based, data loggers, Wi-Fi, LAN cables. It's quite hard to digest. And typically, as a geotech, we are more worried about the piece of soil or tailings that is going through. Then I want to basically from Chris and Mohit, I want your opinion, and I'm going to use something that one of my clients told me when I was trying to explain the client critical state of soil mechanics. He basically said, please stop and give me in 4 bullet points in a really simple term, what is the most important thing to do when you are collecting this data, analyzing the data, and digesting that data? What in your opinion, what will be that important thing, the 4 key elements of handling all these pieces of INSAR, radars, data loggers, and all this information? I would like both of you, your opinion, Chris and Mohammed, if you don't mind, Chris, to.
Yeah, sure. Well, I think Rohan mentioned it earlier. It's very important to consider the future plans for your mine, and when you're looking at new sensors and systems, thinking about how you will integrate that into your monitoring system. So that's one. Another is IT is extremely important. So the geotechnical team on a site might green light a particular solution, and then you might get a whole lot of roadblocks from the organization's IT. So engage the IT early on in the process. They can be critical in ensuring that the project will be a success. In terms of the data collection, automation is really important. Of course, it can be costly, but if we can take the human factor out, it's really critical to success. I've seen it many times where humans are involved and manual data collection is involved. Operating a global integrated monitoring solution can be difficult. So automation is really important if you're looking at a global solution like that.
Thanks.
Thanks, Chris. Yeah, just to add to that point, yes, the first point you need to look for is integrate data management and future plannings. So if you know based on the size of the dam that you're going to having to integrate a lot more instruments than what you have right now. So yes, automation is pretty important. So going back to what example for with Cadia being more than 100 kilometers in total crest length. So it's really impossible. Like imagine he mentioned it's possible to do one full visual inspection per week. That's basically 12 kilometers a day. But imagine having to do that also for collecting manual instrumentation data as well. So that's why automation plays a key role when you're trying to scale the project more. And when you have automated the data, next step is getting the data to the right place. That is the geotech engineers. So the data transmission. So data transmission will again can be done through data loggers, which based on your EOR's recommendation can be every hourly or whatever frequency you want to collect it at. But with that comes the IT side of the data security. So again, it's confidential data. You need to manage it. You need to store it properly. You need to have redundancies in place. So, yeah. And at the end, the fourth pillar would be data visualization parameters. So it's not just important to gather all the data in a single place, but it's also important to correlate and overlay different sensor types together and compare them with each other to make sure that the decisions that you're making are correct and consistent with all the other instrument types.
Thank you. Then sort of a summary for me is understand that the way how you want to collect the data is actually suitable for your site. I really like that early engagement with ITs because typically we don't do that. I've been in that place where we went down the path of selecting a monitoring system and then IT just doesn't, it's not going to work with them and I see we have to abandon that. I think probably just going to open the forum for a couple of questions before we need to yes. And we have a couple in here, 3. I think that's it.
Sorry. What is the role of machine learning and artificial intelligence when applied, in your opinion, when applied specifically to geotechnical data management systems? If you have an idea of that, thanks.
Yes, so okay, thanks for the question. In my opinion, machine learning is basically learning the historical patterns of the data and predicting the future based on the trend lines. And that's basically what its role would be with geotechnical data as well. But again, you'll always have human interaction at the end to verify the models that it has created. Artificial intelligence, in the similar fashion, would can also recommend more instrumentation types that can be integrated or compared with, and comparing it with other historical case studies quickly than having to do it manually.
Have any comment, Chris?
Yeah, look, I'd just add that it's these are buzzwords and a lot of you hear these tossed around a lot, and I think all of our organisations are probably looking at how we can use these sorts of things to enhance productivity. But what I would say is that I don't think anyone's cracked that yet. At the end, we need human interpretation to really from the data. But as soon as we do work out how to use AI machine learning in a way that can truly bring value, and don't want that, we'll let you know.
The same question I was plus you answered right away. A geotechnical engineer is the right person when you have all the data. But all of the geotechnical engineers in the house, everyone appreciates that the data is never sufficient. So any comment on what is the right data and what amount of data is sufficient to go about forecasting, not a postmortem?
Well, typically that would not fall under our responsibility. So we'll provide the data that the designers decide is necessary. But what I would say about data frequency or amount of data is that if you're trying to understand a certain phenomenon, you try to sample at least 10 times that phenomenon. I'll give you an example: diurnal, daily, or seasonal fluctuations. If you're sampling a piezometer once a month, you don't know if you're looking at seasonal changes or you're actually looking at real change or changes induced by operational impacts. So making sure you're collecting enough data, you're sampling enough data to understand certain phenomena like seasonal changes or temperature, it's very important.
Thank you, Chris. I think we have.
I have one question, specifically what you're talking about right now is the sampling interval.
No, I think it's something there.
Sampling interval.
At the same time.
It's up.
I have a question about the sampling interval. In this complete automated data acquisition process, how sampling interval plays an important role, specifically when the deviations are quite significant. Can it be automatically reduced or increased?
Yes. Well, yes, there are certain data logging solutions that can automatically, upon triggering a certain threshold, increase sampling frequency. So there's a variety of products out there that do that. Additionally, with the as battery technology improves and data loggers get better, you can sample at a really high frequency for a number of years on a single set of batteries. So it may not be such a problem that it might have been in the past. We can collect huge amounts of data at a high frequency for many years now.
Yeah, it's pretty much summarized what I'm going to say. But 2 points to add to that would be, yes, there are such data loggers that Chris mentioned, and you can also program the loggers remotely and push programs to increase the frequency if the threshold hasn't been hit naturally. So it's not a matter of you having to go in person to the data logger to program it, but you can do it remotely and have the data at a desired frequency. And yeah, with the point of battery technology, yes, in current state, there are data loggers that can provide data collection at an hourly rate or a daily rate for multiple years without having the need to recharge. So we are already at that point, but it's not going to stop anytime soon.
Thank you, Mohammed and Chris, both panelists. I think David wants to make some announcement.
Yep.
Yeah. Thank you, guys.
Don't go away, you guys. Come back. Yeah, I've actually fallen down on the job over the last day and a half, and what we have got from Incold is some gifts for you and for all the speakers. So I'm going to get rid of these speakers, then I'm going to ask a few more to come up. So if you guys can come down to the front, and you too, Edgar.
Great idea.
Oh, no. Well, I was going to get these ones going first, and then I'm going to get
Yeah, here we go.
But we've got to get the photographs as well, don't you? So
Yeah,
come around.
come on. The photos here.
Thank you very much.
Yep.
Thank you for your comment about the layout of the program. That's very much appreciated. Thanks so much. Thank you for your very good sharing. And so now, just like all the other speakers who haven't had their gifts yet, who have presented, there'll be some more this afternoon. If you all come up now, we'll I'll do my duty. It's going to be a lot big crowd, but that's good. All the speakers from the last 2 days who haven't got a present already. So go out the front door. Hey?
You're holding up.
Do them all at once. Yeah. Okay, next please. Next, please. It's going to be more than that. Okay, so now we can break for lunch. So we really need to be back at 3:15. Yes. So speaking over 3 times a day. Probably. Okay, cool.